Welcome to the industrial backbone of Canada, where the rust tells a story of survival and every rivet holds the weight of a nation's ambition. You stand on a muddy slope in the British Columbia interior, surrounded by the skeletal remains of a cedar forest. Before you sits a steam donkey, a vertical boiler yarder that looks less like a machine and more like a localized industrial riot. The air is thick with the scent of wet hemlock and the sulfurous bite of coal smoke. Every few seconds, a massive steel drum spins, shrieking as a 2-inch cable snaps taut with enough tension to slice a man in half. The mud beneath your boots vibrates with the rhythmic, violent thud of a twin-cylinder engine that knows no mercy and offers no second chances. Think your modern diesel truck is tough? Try keeping a 3,000-ton steam dredge alive in a 40-degree Yukon winter. Or, in this case, try managing a high-pressure boiler that is vibrating at 200 revolutions per minute while a 60-ton log is flying through the air toward your head. So, before we fire up the boilers, take a moment to like the video and subscribe, but only if you find this deep dive into our industrial history valuable. If you or your ancestors worked in the high lead logging camps or survived the era of the widowmakers in the Canadian bush, share those stories below. We honor the grit that built our towns. Now, let's descend into the gears and grease of the machines that built the Great White North. In the early 20th century, the Canadian logging industry was a meat grinder of mechanical ambition. Before the advent of modern safety standards, the failure rate for these operations was staggering. In 1910, a major logging outfit on Vancouver Island reported that nearly 1 in 10 workers would suffer a life-altering injury or death before the end of a single season. This wasn't just bad luck. It was the result of pushing Victorian metallurgy to its absolute breaking point. You are witnessing the high-tension trap, where the power of steam was harnessed long before we had the alloys to contain it. You place a hand on the donkey frame, feeling the heat radiating from the main drum. This machine uses a friction drive system. There are no smooth hydraulic clutches here. To engage the drum, the engineer heaves a massive cast iron lever, forcing a cone of hardwood into a spinning steel housing. The screech is a physical assault on your ears. Precision engineering in 1912 meant calculating the friction coefficient of wet maple blocks against a moving steel surface, while a 30-ton Douglas fir log was dragging through the underbrush at 20 miles per hour. The technical heart of the risk is the high lead setup. Instead of dragging logs along the ground, the cable runs through a massive block, a pulley the size of a wagon wheel mounted 100 feet up, a spar tree. This lifts the front of the log, preventing it from snagging on stumps. However, this creates a literal web of lethal tension. If that spar tree snaps, or if the guy lines holding it fail, the entire mountain of timber and steel collapses inward. You realize that you aren't just standing in a forest, you are standing inside a giant, spring-loaded trap. The human grit required to live in this environment is almost impossible to reconcile with modern life. You see the choker setters scrambling through the slash, the debris of fallen trees, to wrap heavy steel cables around the logs. They work in a state of constant, calculated panic. If the engineer engages the drum before the choker is set, the cable whips, a supersonic blur of steel that can decapitate a man instantly. You watch a worker jump over a moving line with the casual grace of a gymnast. He doesn't look afraid, he looks focused. In this era, fear was a luxury that interfered with the production quota. As the drum takes the strain, the entire donkey engine tilts on its wooden sled. The engineering solution to moving these 30-ton machines was to have them walk by winching themselves forward with their own cables. You watch the timber frame groan, the wood fibers screaming as they bear the weight of the iron. You are witnessing the era where the machine was worth more than the man, and the steam was the only thing that didn't stop for breath. Section 2. Thermodynamics of a Mechanical IED. The heat radiating from the vertical fire tube boiler is a physical wall that hits you long before you reach the iron deck. You are standing next to a pressurized cylinder containing 300 gallons of boiling water, held back by rivets that were pounded by hand in a Glasgow shipyard. In the damp climate of the British Columbia coast, internal corrosion is a silent, microscopic predator. You watch the water glass, the thin tube where the level bounces with every vibration of the engine. If that level drops below the crown sheet, the steel sealing of the firebox, the metal will soften in seconds. The result is a boiler bleave, a catastrophic expansion where the water flashes to steam and the donkey becomes a 30-ton iron grenade. Technical precision in the 1900s was often a race against the limitations of chemistry. These boilers were frequently fed with pond water, a tea-colored mixture of tannin, silt, and organic acids from the logging camp. This water created a thick insulating scale on the internal tubes, leading to hot spots and metal fatigue. You see the engineer tapping the pressure gauge with a blackened fingernail, ensuring the needle hasn't stuck at 150 pounds. In 1905, the Canadian Pacific Railway spent more on boiler treatment chemicals and stay bolt replacements than many European nations spent on their entire mechanical infrastructure. Here, in the deep bush, your only safety is a spring-loaded pop-off valve that could be easily jammed shut by a desperate operator looking for more pulling power. The how it works of the vertical boiler is a lesson in thermodynamic density. Unlike the long, stable boilers of a locomotive, this is a donkey compact, top-heavy, and prone to foaming when the water gets dirty. You watch as the steam is piped through a throttle valve into the twin vertical cylinders. There is no condenser. The exhausted steam is blasted up the stack to create a draft for the fire. This creates a deafening huff, huff, huff that shakes the very marrow of your bones. Precision engineering in this context meant balancing the fireside heat with the waterside cooling to prevent the rivets from weeping. A leaking rivet wasn't just a nuisance. It was the machine's way of screaming that it was about to disintegrate. The human grit required to fire this beast is a story written in sweat and soot. You see the fireman standing on a precarious wooden platform, feeding 4-foot slabs of waste wood into the firebox. He is working in a space where the ambient temperature is 120 degrees, while the rain outside is near freezing. If the mud ring at the bottom of the boiler clogs with sediment, the bottom of the machine can burn out, dropping a ton of white-hot coals directly onto the wooden sled. You realize that the fireman isn't just a laborer, he is a biological sensor, feeling the pulse of the steam through the soles of his boots. There is a dry engineering joke among the old donkey punchers that the only thing more dangerous than a dry boiler is a wet engineer. You watch the main drive gear a massive cast iron wheel with teeth as long as your hands spin with a terrifying lack of guarding. There are no kill switches or emergency stops. If your clothing catches in those gears, the machine will not even hesitate as it pulls you through the reduction train. The only way to stop the beast is to shut the main steam valve, a process that takes several precious seconds while the pistons continue their violent, reciprocal dance. The transition from the heat of the boiler to the cold tension of the cables is a move from one death trap to another. You follow the steam lines as they vibrate with the engine stroke, leading your eyes toward the hull-back drum. The steam is the muscle, but the steel wire is the whip. As the engineer heaves the friction lever, the cable snaps off the ground, shedding a spray of mud and water that sparkles in the dim forest light. You are now moving from the thermodynamics of the engine to the lethal physics of the high lead line, where the real 90% failure rate begins to manifest in the snapping of steel. Section 3. The physics of a flying choker. The physics of a flying choker represents the moment where industrial ambition overrides the natural laws of the forest. You look up at the spar tree, a massive Douglas fir stripped of its limbs and topped with a 2-ton steel pulley block. This tree is the structural anchor for a high lead system that generates over 100 tons of static tension. When the engineer engages the main haul drum, the cable doesn't just pull, it screams. The log, a 60-ton behemoth of ancient cedar, is jerked off the forest floor and suspended in mid-air, hurtling toward the landing at speeds exceeding 60 miles per hour. You are standing inside a kill zone where the safety factor is often a matter of hope rather than calculation. The technical precision of the haul-back system is what prevents the forest from becoming a literal graveyard. This is a secondary, smaller cable that pulls the heavy chokers back out to the woods once the log is dropped. The engineering challenge is maintaining a delicate, reciprocal tension between two massive drums. If the brakes on the haul-back drum fail while the main haul is at full throttle, the cable's bird nest exploding into a tangled web of steel wire that can whip across 100 yards in a fraction of a second. Precision engineering in 1915 meant feathering, a mechanical band brake made of wood and iron to prevent a 100-ton shock load from snapping the main line. The how it works of the cable itself is a study in metallurgical fatigue. These are 6x19 wire ropes, 6 strands of 19 wires each, twisted around a hemp core. You run a gloved hand along a slack line and feel the jaggers, the tiny broken steel filaments that indicate the cable is reaching its elastic limit. In the acidic mud of the BC coast, these wires corrode from the inside out. You realize that you are trusting your life to a rope that is literally eating itself. One specific archive-based fact from the 1909 BC Forestry Commission noted that a snapped high line possessed enough kinetic energy to cut through a 12-inch thick standing hemlock as if it were a stalk of celery. The human grit on the landing is a display of lethal agility. You see the chaser, the man responsible for unhooking the logs once they reach the donkey. He must run toward a swinging 60-ton pendulum of wood while the cables are still humming with tension. He relies entirely on the engineer's ability to hold the load steady on a mechanical friction brake. If the engineer's foot slips or if a friction block shatters, the chaser is crushed instantly. There is a dry engineering joke among the crews that a chaser with all 10 fingers is either a liar or a man who hasn't worked a full week yet. You watch him dive under a log, unhook the bell, and signal for the haulback in one fluid, terrifying motion. You notice the guy lines stretching from the top of the spar tree to massive stumps buried in the hillside. These are the only things preventing the entire vertical assembly from being pulled over by the weight of the logs. The engineering tension in these lines is so high that they hum a low, ominous G-sharp in the wind. You realize that the spar tree is essentially a giant bow bent to its breaking point. If the donkey puncher hits a snag, a buried rock, or a stubborn stump, the tension spikes instantly. The sound of a guy line snapping is often described as a gunshot that can be heard for 5 miles. The transition from the lethal tension of the cables to the internal mechanics of the donkey is a move from the whip to the handle. You step back toward the engine frame, following the path of the wire rope as it spools onto the drum. The steel is hot to the touch, smoking from the friction of the fairleads. You are now ready to examine the gears that translate the steam's heat into this violent, airborne momentum. The machine is a masterpiece of stress, and you are standing at the very center of the strain. Section 4. Metallurgy at the limit of breaking. The internal mechanics of the steam donkey are a masterclass in the limitations of early 20th century metallurgy. You step closer to the main drive assembly, where the bull gear, a cast iron monster nearly 5 feet in diameter, meshes with the high-speed pinion on the crankshaft. In 1910, the science of alloying steel with nickel or chromium was still in its infancy, especially in the rugged, remote machine shops of the Canadian West. Most of these gears were poured from gray iron, a material that is excellent in compression, but notoriously brittle under shock loads. You watch as the teeth engage, a spray of heavy black grease flying from the contact points. Every time a 60-ton log hits a stump in the woods, that shock travels instantly through the cable and into these brittle iron teeth. The how it works of the friction clutch is the most delicate and dangerous interface on the machine. To transfer power from the spinning engine to the cable drum, The engineer pushes a lever that slides the entire drum laterally along a shaft. This forces a set of friction blocks, usually made of kaolin-dried maple or compressed fabric, into a tapered housing on the gear. It is a primitive, brutal version of a modern clutch. If the wood blocks get too hot, they can glaze, losing all grip and allowing a massive log to slide backward down a mountain. Conversely, if they get wet, they can grab instantly, shearing the teeth off the bull gear and sending shrapnel through the air like a burst of grape shot. Precision engineering in this era was defined by the feel of wood against iron. Technical precision was often compromised by the sheer lack of safety factors. Modern engineers typically design lifting equipment with a 5-to-1 safety ratio. In the steam logging era, you were lucky if your gear train had a ratio of 2-to-1. One specific archive-based fact from the 1912 records of the Empire Manufacturing Company in Vancouver notes that they stopped guaranteeing their gears if the operator used double-stacked cables to increase pulling capacity. Yet, in the woods, the donkey puncher would frequently tie down the safety valves and double up the lines just to meet the day's quota. You are looking at a machine that is constantly operating at 95% of its catastrophic failure point. The human grit of the donkey mechanic is what kept these machines from self-destructing by noon. You see a man kneeling in the mud, using a handheld forge and a heavy hammer to peen a mushroomed gear tooth back into shape. There is no such thing as ordering a spare part. When you are 3 days by boat from the nearest foundry, you fix it with what you have, or the camp starves. One dry engineering joke among the grease monkeys was that standardized parts in a logging camp meant anything you could make fit with a big enough pry bar and a blowtorch. You watch him wipe a smear of soot from his eyes, his hands a map of scars from hot oil and sharp burrs. You notice the brake band, a thin strip of steel lined with woven asbestos or hardwood that wraps around the outside of the drum. This is the only thing that stops a log from falling when the steam is shut off. The heat generated by these brakes during a long descending turn is enough to turn the steel cherry red. You see the engineer keeping a bucket of water nearby to douse the smoking wood blocks. It is a constant battle against the second law of thermodynamics. All that kinetic energy of the falling log must be converted into heat, and if the heat isn't managed, the machine will literally catch fire while it's working. The transition from the grinding gears to the high-pitched shriek of the signal whistle marks a change in focus. You are moving from the mechanical gut of the machine to its nervous system, the communication link between the men in the brush and the man at the throttle. In the fog-choked valleys of the coast mountains, sight is useless. The machine must be operated by sound alone, and any mistake in the code is a signed death warrant. You turn toward the whistle punk, the youngest and most vulnerable link in this lethal industrial chain. Section 5. Signal whistles and human error. In the blinding coastal fog of the British Columbia Mountains, the steam donkey is a blind giant, and its only eyes belong to the whistle punk. You look out across the valley, where the spar tree is swallowed by a gray wall of mist, rendering hand signals and visual cues completely useless. The nervous system of this 90% failure rate operation is a simple galvanized wire running hundreds of yards into the brush, connected to a steam whistle on top of the boiler. The whistle punk, often a boy no older than 14, sits on a stump in the middle of the kill zone, clutching this wire. He is the most vulnerable link in the lethal chain, responsible for translating the complex movements of the rigging crew into a series of sharp, high-pitched steam blasts. Technical precision in this communication was a matter of life and death, governed by a rigid whistle code that left no room for nuance. 1 short blast meant stop, 2 meant ahead on the main haul, 3 meant back on the haulback. If the whistle punk tripped over a root and accidentally jerked the wire, or if a falling branch put a kink in the line, the engineer might receive a go-ahead signal while a choker setter was still untangling his foot from a cable. In 1914, a coroner's report from a camp near Nanaimo noted that a single phantom whistle caused by a snagged line led to the deaths of 3 men when a 30-ton log was suddenly winched through their ender. Bunkhouse. Precision engineering here wasn't about the machine's tolerance. It was about the signal's integrity. The how it works of the whistle valve is a study in high-pressure acoustics. You watch as the punk pulls the wire, opening a spring-loaded brass valve that shoots 150-pound steam through a tuned bronze bell. The sound is a physical blow designed to be heard over the roar of the wind and the grinding of the bull gears. However, the steam itself is a hazard. In the freezing winter, the wet steam can condense in the valve, freezing it open. You see the engineer wrap the whistle base in a piece of old wool blanket to keep it from icing up. If the whistle sticks on, the engineer has no choice but to shut down the entire machine, as he no longer knows if the men in the brush are screaming for a stop or cheering for a haul. Human grit in this role was defined by a terrifying level of responsibility placed on the youngest members of the crew. The whistle punk had to remain perfectly still and alert for 12 hours a day, often in a soaking rain that turned his wool coat into a leaden weight. He had to anticipate the swing of the logs and the tension of the lines, knowing that a half-second delay in his signal could result in a snapped guy line and a collapsed spar tree. One dry engineering joke among the veterans was that a whistle punk only graduated to a real job once he'd survived his first cable snap without wetting his trousers. You watch the boy, his knuckles white as he grips the wire, his eyes never leaving the murky shadows where the rigging crew is working. You notice the signal wire itself, a thin strand of iron that is prone to stretching over long distances. To keep the signal crisp, the punk must constantly adjust the slack, a task that requires a delicate touch in a world of brute force. If the wire is too tight, the vibration of the donkey engine can trigger a false whistle. If it's too loose, the signal is delayed. You realize that this primitive telegraph is the only thing standing between industrial production and a mass casualty event. The machine is a weapon, the logs are the projectiles, and the boy with the wire is the only safety catch. The transition from the frantic shrieks of the whistle to the final rusted silence of the abandoned donkey marks the end of the shift and the end of an era. You watch the steam bleed off as the sun sets, the orange light reflecting off the dead man anchors that hold the machine to the earth. You are moving from the lived experience of the lethal risk to the historical reflection on what these failures bought us. The blood in the mud eventually became the ink in the safety manuals of the modern world. Section 6. The rusted architecture of safety. The transition from the violent, high-pressure roar of the yarding shift to the silence of the forest floor is a descent into a mechanical graveyard. As the last of the steam bleeds from the donkey's valves, the ticking of cooling iron is the only sound left in the valley. You stand by the rusted drum, looking at the grooves worn into the steel by miles of abrasive cable. This 90% failure rate was not just a statistic, it was a brutal, daily reality that eventually broke the tolerance of the Canadian public. By the late 1920s, the sheer volume of widowmakers and boiler explosions forced a radical shift in the relationship between the engineer and the law. You are standing on the literal birthplace of modern Canadian industrial safety. The technical legacy of steam logging is written in the Boiler and Pressure Vessel Acts that now govern every factory in the nation. One specific archive-based fact from the 1890s reveals that before these regulations, a second-hand boiler could be sold and operated with almost zero inspection, leading to hundreds of preventable deaths. The catastrophic failures you've witnessed today, the sheared bull gears, the primed cylinders, and the snapped guy lines became the case studies used to develop the first rigorous safety factors. We moved from a 2-to-1 margin of error to the standardized 5-to-1 and 10-to-1 ratios that keep our modern cranes and elevators from falling. You realize that every danger high-tension sign in Canada is a tribute to a man who didn't hear the whistle in time. The human grit of the steam era didn't vanish. It evolved into the professional pride of the modern trades. You see the donkey puncher bank his fires for the last time, his face a mask of grease and exhaustion. He belongs to a generation that mastered the most temperamental power source in history, surviving on nothing but intuition and a steady hand on a friction lever. As the sun sets behind the jagged peaks of the Coast Range, the orange light catches the skeletal frame of the spar tree. It looks like a monument, a wooden spire dedicated to the thousands of workers who traded their safety for the timber that built our cities. The era of the steam donkey was a localized industrial revolution, a brief and bloody chapter where the scale of our ambition far outpaced the strength of our materials. But as the shadows stretch over the rusted winch drums, you see the connection between that chaotic past and our structured present. The lethal risks of the 1900s forced us to become better engineers, better observers, and ultimately a more compassionate society. We reflect now on the ghosts in the machine, the whistlepunks, the choker setters, and the engineers who lived and died in the web of tension. They are the silent partners in every modern Canadian project, their hard-won lessons built into the very rivets and codes we use today. You step away from the cooling iron, leaving the machine to the moss and the rain, but carrying the weight of its story with you. The Great White North was built on steam, but it was forged in the fire of survival. Would you like me to generate a detailed technical diagram of a 1910-era vertical fire tube boiler to illustrate the internal risks discussed in this documentary?